Hey everyone, and welcome to the Foundry by Forge College. I'm incredibly excited for today's explainer because, well, it's basically a high-stakes detective story. If you've been following along with our journey through FireDancer, you know we just finished tuning our validator's race car engine. By that I mean we successfully optimized our data management. But we have a brand new problem. Out on the track, our transmission, the consensus mechanism, is suddenly stuttering. Why? Well, today we're going to find out.
To solve this, we'll be tracking down these regressions in 6 logical steps. We'll start with the performance mystery, move to setting up your lab, compare baseline versus candidate runs, gather our evidence, find the root cause, and wrap it all up with the debug report.
Let's kick things off with Section 1, the performance mystery.
So, in our last optimization round, we started buffering and batching account updates to reduce disk I/O contention, right? But doing that actually altered the timing at several critical integration points with the consensus layer. This resulted in a regression. Basically, that's a software bug that ruins a feature right after an event, like our recent system optimization. Honestly, a regression is just the universe's way of punishing you for making your code faster in one place by breaking it entirely somewhere else.
All right, moving on to Section 2, setting up your lab.
Before we can put on our detective hats, we absolutely need a highly controlled environment. Think of this as your mechanical parts list. It requires 4 main things. First, our FireDancer validator binary. Second, Bench TPS, which acts as our synthetic transaction generator to produce a nice steady workload. Third, Prometheus and Node exporter for our telemetry pipeline. And finally, our flame graph tools for profiling our CPU stacks. You need all of these running smoothly before you even think about starting a test.
Which brings us to Section 3, baseline versus candidate runs. Now we jump into the A/B testing phase. We start with a baseline run using a known good commit and a steady workload. You'll want to capture 3 steady-state runs to completely eliminate statistical noise. Then we compare that against a candidate run using our freshly modified binary. Let me stress this. It is absolutely critical that the workload and metric capture commands are identical. If you don't use identical scripts for both sides, you're literally just measuring noise, not real performance.
When comparing these runs, P99 latency is one of the most important metrics you'll look at. It's the latency threshold that 99% of transactions fall below. Think of a busy restaurant. Your median latency is how fast most tables get their food, say 15 minutes. Not bad. But your P99 latency? That's the poor customer sitting in the corner waiting an hour because the kitchen got unexpectedly backed up. In high-performance validators, tail behavior is a crucial metric because it exposes hidden contention in the system.
Now for Section 4. Gathering profiling evidence.
Once we spot a shift in the numbers, we need concrete proof. Look at the median TPS. It shows a very slight, almost negligible drop. If you only looked at the median, you'd probably think everything was completely fine. But check out the P99 latency. It shows a massive 40% increase. A tiny drop in throughput alongside a massive spike in P99 latency is a huge red flag. It's clear-cut evidence of increased contention or newly introduced bottlenecks.
To catch the culprit red-handed during that exact regression window, we use a flame graph. This is a beautiful, low-overhead visualization of profiled software that lets you identify the most frequent code paths and CPU hotspots quickly and accurately. And yeah, it literally looks like flames. The wider the flame, the more CPU time that specific function is burning up.
Moving right along to Section 5, finding the root cause.
Now it's time to put on our judge's robe and assign blame to the actual failing subsystem. One key piece of evidence you might notice in your system telemetry is called I/O wait. This is just the time the CPU spends completely idle, twiddling its thumbs, waiting for input or output operations to finish up on the disk.
We can actually use metrics like I/O wait to map the regression to a specific subsystem. For example, if you see increased I/O wait, serialization hotspots on your flame graph, and reduced write throughput, you are almost certainly looking at a data management issue. On the flip side, if you're seeing increased lock contention in the consensus modules, a higher queue backlog, or network stalls, then your regression is a consensus interaction issue. This mapping is just so vital because it isolates exactly where your recent optimization created backpressure.
And finally, Section 6, the final debug report.
If you look at the advanced courses and learning programs over at Forge College, they heavily emphasize this exact rigorous methodology. The entire engineering process culminates in writing an airtight debug report. You're going to need your environment details, your exact artifacts, meaning the binary and the specific git commit SHA, the commands you used, raw metric snapshots, computed deltas, profiling output like your flame graph, and a short root cause analysis. The goal is simple:
Another engineer must be able to perfectly reproduce your experiment without ever having to guess what you did.
To guarantee that reproducibility, your report must include a script of the exact steps, like 1. Start Prometheus and the exporter. 2. Start the baseline validator. 3. Run the bench TPS workload. 4. Capture the metrics query. 5. Repeat for the candidate binary. Let me be unequivocally clear here. A vague bug report is fundamentally useless. These exact, reproducible steps are the lifeblood of operational efficiency.
Lastly, your report has to include a remediation step, and it must be measurable. You shouldn't just wave your hands and say, hey, we need to fix the flush. You should predict something like a 15% CPU reduction when swapping a synchronous flush for a batched asynchronous one. You have to give the team a concrete, testable metric to aim for, based on your profiling evidence.
Which brings us to our final, provocative question for this explainer. How do we balance these architectural trade-offs? Because think about it. If we optimize our data management perfectly, but we accidentally starve our consensus mechanism in the process, are we really winning? In our next lesson, we're going to synthesize these trade-offs to build a truly efficient, harmonized validator. I highly encourage you to visit forge.college to explore this explainer and dive into other fascinating Web3 topics in much more depth. Thanks for joining me on this detective hunt today, and happy debugging.